we have Gwen Spencer. Gwen is the operations research scientist, is an operations research scientist at Convoy, and Gwen is presenting network science from beautiful mathematics to driving real world decisions. And Gwen, just a reminder to start your timer, of course, and enjoy.
Okay, great. Can people hear me?
Yes.
Victoria, yeah, thanks, thumbs up. Cool, so I'm Gwen Spencer, operations research scientist at Convoy. It's a different flavor of data science, but I think you'll recognize things that you know.
Oh, Gwen, you went on mute.
Oh, what about now?
Yeah, you're good.
Okay, thanks. Cool, so I'll start by telling you about how I fell in love with graphs at age 19, what I liked about them, and then I'll talk a little bit about networks as a modeling tool, what they're good for, which is settings where there's spatial heterogeneity and connectivity or flow. And then I'll talk about some work that I've done at Convoy on trailer rebalancing, which is basically just trying to efficiently route supply to meet demand in our trucking network. And before I jump in, I want to also go ahead and say thank you to some of my teammates. So you never really are able to put a system into production without an interdisciplinary team. And I'm going to credit just some terrific engineers that I work with, as well as some really insightful folks on our ops and fleet management side. Cool, so when I first met graphs, they were a beautiful, clean object. In particular, they were defined just by a set of nodes, which I'll draw as these points, and a set of edges, which I'll draw as these lines. And a key thing to remember about a graph is that the drawing is actually not the graph. So this is the same graph as this. I've just changed the drawing, and it's the same graph as this. I've just changed the drawing again. So graphs are a really engaging setting because you have these like really cool spatial and visual tools, these drawings that you can use to get good ideas. But actually what's even maybe a little bit more savory is that there's some subtle properties that aren't captured by most of the pictures you draw. So you actually have to work hard to avoid being outsmarted by your own pictures. I think that's something I've always loved about graph theory. So you can also decorate graphs in a number of ways. Instead of having these plain edges, I could have directed edges that say something about how flow can travel through this graph or this network. And you can also ornament edges in a number of additional ways. So you can parameterize them with a notion of distance or cost to travel along each edge, or a notion of capacity in terms of like how much flow could travel along a particular edge. Also, in addition to these parameters that sort of define the graph, there's a lot of interesting ideas around not just sort of the definition of the graph, but the macro properties of a graph or a network. So here I've drawn a suggestive picture to sort of describe or motivate the idea of dense communities that maybe can be separated by narrow cuts. By narrow cuts here, I'm referring to the fact that there's a few edges that I could remove from the graph that would disconnect these dense communities. And something that you might be thinking about already is the question of, without this nice picture, without this nice drawing, how would I detect this kind of macro structure? Another thing is that graphs are generally sort of thought of as static, but for a lot of real applications, graphs actually sort of evolve over time. Connectivity evolves over time. So maybe on Monday, you have some structure that's defined by sort of dense local communities that are linked by just a few long edges. But by Tuesday, some of those edges have left the graph. Maybe some new edges have entered the graph. By Wednesday, things are looking pretty different. And by Thursday, things are starting to look quite a bit different still going into the weekend. Okay, so networks are a really versatile modeling tool, and just some settings in which I interacted with networks before I came to industry include things where, for example, the nodes represent locations on a landscape and the edges indicate something about what spread is possible. So some settings I had thought about were things like, for example, the spread of wildfire, the spread of invasive species, or even actually when you had a species that you wanted to spread, for example, like an endangered species, and you're trying to build a conservation reserve from which it's easy for those species to spread out. Another hot topic is social networks where the nodes are humans, and there the edges indicate some kind of relationship. We're all getting sort of a crash course right now in epidemiology, but these models are also studied in viral marketing, the spread of information, models that verge actually on the econ space that have to do with the stability of norms and the spread of good and bad behaviors, et cetera. So what does this all have to do with trucking? I work on a product at Convoy, which is called drop and hook shipping. And the idea there is as follows. So there's actually a decoupling of the trailer from the cab of the truck. And Convoy is responsible for delivering those trailers on site to a shipper yard 24 hours before the pickup of the shipment. The idea of this is that you can basically then just have the driver come with their cab and pick up a loaded trailer, and there's no waiting. So it basically avoids the problem of delay backing up into the shipper operations or vice versa. When there are delays on either side, this kind of drop and hook product decouples those. So what we're responsible for is delivering these trailers on site before pickup. And to do that, across North America, Convoy has to maintain a universal trailer pool of thousands of trailers to serve these shipments. There's other rebalancing settings that people are generally familiar with. So rebalancing comes up because the pattern of shipper loads that we need to transport is not perfectly balanced. So just with like a bike share operation where some people want to go one direction more than the other direction, some of our shippers want to send goods one direction more than the other direction. Something you could easily imagine is like the Port of Los Angeles. There's a lot of outbound shipments, a lot more than there are inbound shipments to the Port of Los Angeles, for example. So the pattern of shipper loads is not perfectly balanced, and that means that basically trailers can build up in some parts of our network and become very scarce in other parts. So we have to do something to correct that. So to provide this product efficiently, we basically have to do two things. First, we have to make sure that we're not maintaining a larger trailer pool than necessary. So we lease these trailers. They're expensive. We don't want to be spending more money than we have to, basically obtaining that capacity. And secondly, one of the things we really don't want to be doing is just moving around empty trailers. It's really wasteful in a lot of senses. It's like both expensive for us to find drivers to do it, and also it's just like moving around a large empty box is pretty unsustainable. So we'd like to avoid that whenever possible. So this brings us to the topic of trailer rebalancing. So let's talk about the network here. So the nodes are effectively our shipper yards. This is just a schematic here. We actually work with hundreds of different shipper yards all over North America. And each of those nodes has some desirable behavior that we're aiming to maintain. So at each node, there's basically a limit on how many of our trailers can be at that shipper yard. And then there's also sort of a requirement called the preload requirement here. That's how many trailers we need to have on site for the outbound loads to be served appropriately. And then our job is to manipulate that blue line that you see, which is the supply of available trailers. Okay, and in particular, we're looking out a little bit more than a week into the future, and we're trying to make sure that our available trailer supply is going to be between the max defined by the yard and this preload requirement to serve the outbound shipments. So the question is, what mechanisms do we have to keep that trailer supply in the desirable range? So at each of those nodes, at each of those yards, we have to avoid two bad events. The first event happens when basically there's more trailers flowing out than there are flowing in for some extended period. So if that's happening, one of the things that can happen, right, we have a net outflow that's sustained, right? We could run out of trailers at that site. And this is a pretty serious service failure for us. So unlike a rebalancing setting with like bike share or something, if there aren't bikes in a certain region, it just means that the company loses out on the opportunity for people to use bikes. But for us, if we've made a commitment to serve these shipments, it's like a very embarrassing thing for us with our customers to not actually be able to provide the trailers. Potentially, we can churn shippers in this way if we're not able to provide this like very, very reliably. Okay, another kind of bad event that could happen is that for a sustained period, it could be the case that the flow into the yard is larger than the flow out of the yard. And in this case, what can happen is we could violate what the yard has told us about how many trailers we can park on site. So that's actually also kind of a bad situation for us. Sometimes we have to spend a lot of money to really quickly move trailers out of the yard if we've let this happen for some period of time. Great, so what flexibility do we have in order to maintain these trailer supplies in the right range? So in particular, what we can decide is that after a particular shipper shipment, we can decide where the empty trailer should get returned. So imagine that the original shipper shipment is this shipment from Seattle to Spokane. So it's about 280 miles. And then afterwards, we could leave that trailer there in Spokane, but we could actually take it somewhere else. We could ask the driver to take it somewhere else. So for example, we might consider 3 different options here where the empty trailer return, the first option goes down to Richland, that costs some amount of money. The second option, it goes to Yakima after the drop off in Spokane, that costs some amount of money. Final option, it could go to Pullman, maybe that costs some amount of money as well. So each of these options costs a certain amount of money and it incurs a certain number of these empty miles where there's just this empty trailer being transported. Great. So our goal here is to select a globally optimal combination of these empty trailer returns to offer through our marketplace. So we have to tell the driver what shape of job they're going to be bidding on. And we'd like to select those shapes of jobs in a coordinated way over our entire set of shipments. Great. And so I'm showing you here a picture. I'm showing you these maps, but the picture is not the graph, right? So let's jump to the graph. So it's very much like a directed graph that's sort of making choices. We're making choices about how these trailers are going to flow in this directed graph. And we have some parameters attached about the cost of each kind of move. So what we're effectively doing here is we're selecting sort of a globally optimal combination of these directed edges. Great. So what we use to do this is a algorithm that we call TRIP. So this is the trailer rebalancing integer program. So in operations research, integer programming is like one of the most classical tools, right? The name of the game is that you model a problem as an integer program and you can use off-the-shelf solvers. And what we use here is just Google OR tools. Once we've formulated the mathematical model in the right way, it can solve a very large problem very quickly. So we feed this algorithm all of the shipments in our network, the current GPS location of every one of our trailers, and all of these different options about where the trailer returns could go. And the output is what jobs we should offer to drivers in our marketplace. Okay. So the final comment that I want to make here is, we have this system that's going to sort of plan what our marketplace offering should be. But something to note is that the set of shipper shipments is sort of always changing, right? So on Monday, it's going to look different than it looks on Tuesday, on Wednesday, on Thursday, et cetera. There's always new shipments being awarded from shippers. And also our trailers are always moving around, sometimes in ways that we expect and sometimes in ways we don't expect. So trailers can break down. They can also just kind of go rogue. It can be the case that the driver just sort of drives off with them. And we have to actually track them down on a much slower twitch schedule. So we actually have these inputs that are sort of evolving over time. And the way that we currently cope with that is through regular replanning. So basically we make a plan about what the marketplace should look like, and then we replan just a few hours later and change up our plan every couple of hours according to the new information that's arrived. So some significant issues there include questions about how predictable beyond the set of awarded shipments, the set of shipments could be, and is it predictable sort of at the scale that's actually relevant to our decisions? So I've plotted here a number of shipments that we have over the course of a week, and you can see like a nice weekly cycling, and that's when we aggregate over the entire country. But the kinds of decisions I was telling you about are at the level of individual yards. So in order to make good use of prediction, we need not just consistency sort of at this aggregated national level, but actually at yard level. And it turns out that's not something we can always expect, right? So we have to really be aware, right, that the level at which the phenomena that influence our inputs are predictable may not be the level that we need for the decisions we want to make. And finally, I think there's also some questions here about how to innovate deliberately. So the idea that every output depends on an input, right? But some outputs are not that sensitive to certain inputs. So when we talk about improving sort of the quality of our prediction, for example, like trying to predict better when a trailer might break down, we have to ask, like, are the outputs, are the optimized decisions actually like actually sensitive to the breakdowns of individual trailers, for example. Great, so hopefully I've given you some flavor of this problem, and I'll go ahead and stop there and take questions.
Thanks for the talk, Gwen. So just a reminder to everyone, if you have questions for Gwen, you can go ahead and post them in the Q&A. And we'll give you a couple minutes just to formulate some, and if not, we'll give you a quick break.
Yeah, cool. So the first question here is about how ML techniques are integrated into these network optimization problems. Yeah, terrific question. So a lot of the parameters in the optimization problem that we write down are actually the outputs of ML models. So in particular, one that you could think about immediately is the price that it's going to cost us to serve those different options, right? I showed you sort of a panel of 3 different options. So in order to reflect on which ones are kind of the best deals given the constraints that we have to have some notion of what we're going to be able to find in terms of paying a driver to do each of those options. So I think that's kind of like the most salient example. Here's a very flattering question. How did you become such a great speaker? Yeah, thank you for the compliment. I was actually a professor for about 4 years. I was a math professor in liberal arts college back east. So I had lots of practice trying to maintain the attention of a captive audience. Okay, great. So I've got a question here at the top. How often do we run into multiple solutions that are equally good? And what is sort of the structure of those solutions? Great question. So definitely in optimization, it can happen that there's sort of ties. We actually haven't really looked carefully at that in the sense that we implement the optimal solution that's returned, but you could ask something like, is it the case that every solution that's within 1% of the optimal is effectively the same? Or is there actually sort of diversity in the patterns across those near optimal solutions? I think that's a question that we'll likely get to when we start to think about offering multiple overlapping options in the marketplace. I've got a question here that says, how robust is network optimization to anomalies? In the current case of COVID, how quickly can the formulations pivot? So super timely question. We actually were piloting during the initial COVID surge. We transport an incredible amount of consumer goods, and we do a lot of business with companies that transport like staples that there were sort of rushes on during the early COVID period. This system is basically able to look at the set of awarded shipments and work from that. We weren't actually trying to predict, like it would have been very, very hard to predict that kind of volume surge that we saw in the COVID period. This sort of says, let me look at the set that I've been awarded. That goes out about 5 or 6 days. And we did find that it was able to kind of cope with this historically unprecedented level of business. Question here at the top, what challenges did you face in formulating the problem so that it could be solved efficiently? Or did it turn out not to be that important? Or sorry, there's several things for me to parse here. So I'll just start with the first part. So I think that there's always, when you write down an integer program, there's sort of smaller and larger ways to write down the formulation in terms of what variables you include. So for example, one option that you have is to give every one of these thousands of trailers its own unique name. We don't do that. We consider the trailers both in name and sort of in the model to be universal. So we consider them to be fungible. And that allows us to write down a much smaller model that can be solved really quickly with this open source Google OR tools tool that I mentioned. And then a second part of this question was, was it the case that the replanning and the real world complexities were sort of much more dominant in terms of the challenge? So absolutely yes. Like the bottleneck here is not sort of the problem size, or rather it was not that hard to write down a problem